Today we're going to talk about some use cases that we've built up around using the Raspberry Pi as an edge device for both integrating custom data as well as sensor-based data into our middleware stack. The first part of the talk, I'm going to go over how I created the Bluetooth scanner that we used during the demo, the keynote demo in the middleware. And these are the devices you've probably seen stuck to various walls in the sides of rooms throughout the conference, and it's what we use to generate those approximately 7 million events of data from just 300 scanners over the course of less than 48 hours. And that's 48 hours real time, total time, but probably only maybe 16 to 18 hours of actual presence. So just a few devices can really generate quite a bit of data. This is the motherboard of the Raspberry Pi 2 system. This is the little computer that is the heart of the demos and the Bluetooth scanner. And what that consists of is basically a little Linux system with now a gig of memory, a quad processor. In this particular example, we were developing with Raspbian, but we also tested with Pydora. There's several different operating systems based on Linux that you can put on these devices right now. It supports 4 USB ports, a 10/100 Ethernet port, a 40-pin GPIO header, and the persistent memory storage via an 8 gigabyte. Well, we used 8 gigabyte SDHC cards, but it just has a little micro SDHC card. So whatever capacity you can put in there is what it will take. We only needed 8 gigabyte. You can get, I think, up to 64 gigabytes or higher these days with those micro SD cards. This was a class 10 card because one of your limiting factors in terms of how rapidly you boot up and how rapidly you access your persistent data is dependent upon the class of the SD card. We put a full development environment on that to build the various libraries for our middleware stack, because we were working with some of the bleeding edge, newer patches to various things that we were testing out. So we actually built all the libraries right on the Pi itself. And with the Pi 2s, that's actually not terribly difficult. There are some larger libraries that can still take a while, but in general, it's pretty easy to just build your own development environments and libraries and software right on the Pi itself. You can certainly look at using cross-compilers if you're building bigger systems, but for our use case, we didn't need to do that, and it simplifies development. So the actual scanner used in this use case was a Bluetooth beacon, which if you weren't at the keynote, it's one of these little devices. This is a Bluetooth for low-energy device that is produced by Gimbal, which is a division of Qualcomm, split off from Qualcomm and is getting into their, I guess, sensor space. It's a $5 device, which is a bit unusual. Most of the Bluetooth sensors that act as beacons are in the range of $20 to $30. So it's by far the cheapest device, which is why we went with it. We have no idea what it actually costs. It probably costs at least that much to manufacture. They're probably selling it at a loss to promote their business, but that's why we went with it. And how it works is it emits a standard advertising packet. So in the Bluetooth low energy spec, they define several different data formats, and one of them is called an advertising packet. And there's several different types of advertising packets that dictate what the format of the data is. And the use case for that most manufacturers work with in terms of the beacons is it uses the iBeacon format that Apple is promoting. And that's tagged in terms of the type of a Bluetooth advertising packet is called a manufacturer-specific data. So it's completely arbitrary. So you really have to know what Apple has defined as the iBeacon format, to be able to identify it if you're creating a scanner that's looking for iBeacons. So for example, iBeacons from either iPhones or devices or Apple-specific devices, or as well as other people who have signed up to be iBeacon manufacturers or producers. That's the format that we'll use. Fortunately, that format happens actually to be proprietary. It's just that so many people have put it out on the internet that you can figure it out. You can also, take a look at what the format looks like with a Bluetooth low energy scanner that TI sells. So that's, some of the stuff I did early on was just try to figure out what exactly was in there and, what was useful about that packet format. But essentially it boils down to there's a 16-byte UUID and a major and minor ID. So that's all that advertising packet contains. So it's basically just a simple identifier that you then have to, via another mechanism, associate with location or a person or some other, whatever information you're looking to convey via that beacon. There has been some talk about standardizing that to make that a little more open and less opaque through a Bluetooth working group, but we'll see. So that's our sensor. Now let's get to how we actually built the application on the Pi to consume that sensor data. So the first thing I started with was, could we actually do this processing in Java? Because ideally I prefer to work with Java in terms of its ease of use and debugging, multi-threading, as well as integration with our middleware layers is typically easier. And originally, so on the Pi, the primary Bluetooth stack is the BlueZ stack. So if you've installed a Linux distribution that supports Bluetooth, you're typically going to find the BlueZ stack and its tools, which include an implementation of the host control interface from the Bluetooth specification. And so it has various tools like HEI config, HEI tool, and HEI dump that allow you to configure that stack and then take a look at the data that's coming out of it. And originally, I wasn't going to integrate very deeply into that. I was just going to try and use the HEI dump command, which can be put in a raw mode, so you could just see the raw packets coming in, and I would just stream that into a Java process and parse those, basically the text output from that command. Well, it turned out that that was a little bit too computationally expensive or wasteful. So just a few beacons were taking quite a bit of CPU just to process basically a text stream, which is not trivial. I mean, like I said, we produce millions of events from one beacon. If you let it run for 24 hours, you can easily probably produce on the order of 2 million beacons just from one scanner. So you scale that up to 300, and you generate millions of events a day just for one scanner. Mostly the problem is that the JITs on the Pis are not very good. So the default, the OpenJDK JIT doesn't exist. So it's just a pure interpretive VM. Oracle actually does have a VM for the Pi that does have a JIT, but it's still not that great. Testing it is a lot better than the default one, but still not back to your typical performance you can see on your usual server-side JITted VMs. So I'll talk about how I actually ended up integrating natively with C++. And at this point, now that I have that native integration, I could probably take and wrap that basic processing of the events from the Bluetooth stack and wrap that in JNI and then go back and write the rest of the infrastructure around that. I think that would be a lot easier to maintain and advance going forward. I may look at that at some point, but what we ended up doing for this particular use case is a pure native C++ integration on top of the BlueZ stack. So where we started, again, was we just downloaded the current BlueZ stack to get the source. And then I took a look at how exactly that HEI dump command was processing the events that it was pulling off of from the Bluetooth dongle. And really, it boiled down to just one file, heidump.c, that includes the processing of the advertising events as well as the various other types of events. But I was specifically only interested in the Bluetooth advertising events that the beacons emit. We just put in, a simple callback mechanism so that you could dispatch that out to whatever framework you wanted to wrap around it. And then, so it had been about 20 years since I'd actually worked with C++, so it was interesting to get back into what the standard C++ libraries had actually made available in terms of threading, pointers, locks, and all that stuff. I was actually pleasantly surprised. Actually is not as bad as I remember having to do this stuff way back when. Certainly not as easy as Java, but it's far from, do everything yourself that I had to do in the past. So, the code really is not that bad. Really the big issue with C++ is it just still continues to be difficult to debug relative to Java in terms of, if you do have a memory leak, if you do have a memory access error, if you've made a mistake, it's the usual. Okay, well, how do I debug this issue? But overall, I was really quite pleased with the state of C++ as of the standard 11. So if you actually do end up pulling down the code and take a look at that, you'll find it's really not that much code. And really, the core of the scanner is just a few classes, again, built around the Bluetooth stack and the code from the HCI dump command. That basically was just turned into a simple main entry loop that's pulling the advertising events from the Bluetooth dongle and passing those out via callback, which then comes back into the main application control layer, which consists of basically a dump parser, which is taking those events and doing a little averaging. Because in general, the events, are mostly highly redundant, highly repetitive. Even just walking, even running. I mean, if you run past a scanner, you're going to get picked up a few times a second within, each meter that you can move. So there's a lot of redundant data, and in general, one of the things that we were seeing when we started having multiple scanners is, well, two things. One, the RSSI signal, which is part of the advertising event that the Bluetooth stack returns to you. So basically, it's a measure of the strength of the signal that it picked up, is very variable. And so when you have multiple scanners and multiple beacons, even stationary, the RSSI moves, jitters around quite a bit. And when you actually are moving it or positioning it in between yourself and the scanner, your own body in the scanner, water attenuates the signal quite a bit. So we really needed to do some type of averaging of the signal even on the pies. In other words, we'd be pushing even more information out to our AMQ broker and requiring even more averaging and filtering from the signal at that level. And again, the Pi, actually had plenty of processing power when we wrote it in C++ to deal with these events. I mean, so our worst case, if I had all of our 300 beacons sitting on top of one scanner, the maximum CPU load I would see is maybe 25%. So they have plenty of reserve horsepower to deal with this particular use case. So we did introduce or averaging and also time windowing, time boxing of the events into windows of 1 second is what we ended up going with here. We do further time averaging at the Spark and our Spark engine layer in the cloud later on, but just in terms of the scanner itself, we do have some time averaging and time filtering to simplify the data that's going out, and also it was helpful for debugging. We did have a mechanism, so actually the scanner that we had up on stage in the keynote was connected to an LCD display, so that was another mechanism that we used to debug, what was the status of the scanner itself. And also for testing on, how well it could actually filter out different beacons. So if we moved, you can move into the scanner as we did, again, in the demo last night, it would lock onto different beacons based on their RSSI signal strength and display information about that beacon, as well as the status of the scanner itself. Because there are early on in development there were circumstances where we would have memory leaks or other issues, and so it was helpful to have the memory usage and that type of CPU usage displayed on the scanner itself via an LCD display. But the main function of the infrastructure around the Bluetooth HCI dump loop was to do that averaging and then push it back to our message broker, which we had a pluggable architecture, so we could try different protocols. So we tried several different of our messaging protocols back to our AMQ broker, and we ended up using the Cupid AMQP version because it was the most stable and had reconnection capability features. So one of the things that we learned early on, so in my house I have several different Wi-Fi networks, and depending upon where the scanner was, you would lose it periodically. Fortunately, we ran into that and had developed some tolerance to that, because here in the conference center, it was terrible. You know, even sitting right next to a Wi-Fi router, we would lose the signal, you know, even on a laptop. So the signal here is quite unreliable. So you needed a capability to lose a connection, store your messages or your events that you're still getting, and then when you reconnect back to the broker, have those forwarded. So that's a feature that we just got for free, essentially, with the AMQP Cupid C++ library. So to get, if you're interested in looking at the source code, this is what I'm showing here is the link. So the exact scanner code that we ran on that we did run during this conference and that we're demoing during the keynote is available in this repository. So you can go take a look exactly what the integration with the BlueZ is, as well as the code that we wrote, and what our integration with our various messaging libraries is. There's a number of different directories in that GitHub repository that I'm not showing here, because they're basically were for testing or other, other experiments that weren't relevant to what we ended up running. So the main one would be the bin one for the various scripts to start the scanner in different modes, because you can run the scanner in several different modes. One would be a simple analyze mode, where it's basically just dumping out the beacon counts that sees closest to it, as well along with their signal strength and counts. So that's just useful for the initial debugging. There was a battery test mode, so that we can see how long the batteries in these things lasted, because it's actually not that great. Typically, it's going to be 6 or 7 days before the beacon runs out of power. It's not that great a sensor relative to what you would typically expect. And what some of the more expensive beacons, that's one of the features that they add is much longer battery life. So for example, Gimbal also has a $20 beacon that they claim will run for 3 years, okay, versus 6 days. I mean, this beacon is particularly bad, and I think they actually have some firmware issues that they acknowledged when I originally was talking about, why is this so bad, and this, why is the battery life so bad? I think there's some, firmware issues that they could improve upon. But that's one of the main things you got to deal with in terms of these battery-operated sensors is, are you going to have to service them frequently? And in this case, actually, these would be not usable except for short-term conference-style use cases. So for the use case that Burr mentioned in terms of a warehouse with pallets on it, these would be completely, unusable, because you'd have to go replace the batteries every week. The LCD directory in that is simply code for hooking up to an LCD display using the wiring Pi native library. It's not required. There's actually an alternate. There's a facade on top of that allows you to display the information different ways. README gives you actually a pretty good description of all the requirements. So there's a ton of additional libraries that had to be installed on top of the base Raspbian and Pyadora images. And so I go through all of the requirements and how to build the various libraries. Some of them were source solo requirements, and also we built our own messaging libraries on the Pis as well. So how to build our own Cupid library, and Proton library, for example, is in there. Source is the core, was the original core when I was trying to actually just do the text processing based thing, but there's, so the basic definition of the beacons and the basic call-outs and infrastructure is defined there. And source 2 was when I went and did the full-blown native integration and added the multi-threaded architecture with averaging of the beacon signal, as well as boxing it into time signals and stuff like that. And this was added in that layer. And then the last interesting piece is the systemd directory, which is just the service definitions for integrating with the operating system in terms of starting various services up at boot time. Because, for example, what you need to do to enable, by default, the BlueZ stack doesn't just automatically start emitting the low energy events. You have to put it in a state where it says, I'm interested, I want the stack to scan for low energy events, and that's what triggers the behavior of HCI dump to be able to pull those out. Various other things we did was, for example, again, because because of the sketchiness of wireless networks in general, there's a script and a daemon that will run and test. Can I ping my gateway? If I can't, then I'll simply recycle or refresh the network interface using IF up and down. You know, that was a common thing that we had to do to make sure that the scanners had better connectivity, or, you know, could recover from whatever. They would lose association with their wireless gateway. You know, it was the typical problem that we would see. There's a couple other just simple things. Like one of the first problems is, how do you know what your IP address is if you haven't pre-configured your router to specifically assign a given IP to a given MAC address. So there's a simple utility that starts at boot time that you can plug in, you know, a headphone or a speaker to the Pi, and it will emit using A-Play. So it will speak the IP address, which is useful. And we'll actually see that if you guys come to the hackathon. You know, that's the first thing you have to do is how do I SSH into this little device as it boots up on the network. And then the last thing is the service script to run the scanner. That's all I got at this point. So if you have any questions in terms of details relative to our experiences or what type of integration was required, I can take it as at this point. In other words, we'll move on and look at more specific traditional IoT examples in terms of accessing other sensors. So essentially here was effectively a protocol gateway. I mean, that's, you know, there was no interfacing with the GPIO pins. It's basically you have a little Linux box, and we integrated with a protocol stack, and then transferred it over to IP and in more particular JMS. More particular messaging infrastructure. We didn't actually use JMS. Okay. Yep. It's just the client library. Yeah, just the client. Yeah. When you enable the reconnect feature. So by default, that's not the default. That was just a flag that we enabled, you know, to have it reconnect on failure.
Try to plug in and see if this works.
Yeah, let's switch.
What'll happen when I connect? Good. All right, if you guys don't mind, I'll stay seated for a second since I gotta get access to this laptop. The keyboard. Space. Prepared for me. Great. Linux box works and Mac doesn't. That's a,
There you go. It's up.
all right. Trying to move this other wire here. This is the problem with IoT demos. Hardware is hard because you got to carry a lot of hardware. Okay, let's actually start with a demonstration because I think it gets more interesting if we start with demonstration.
You got to mirror that to the external display or something.
Come here. And now I've lost the mouse. Is it over on the other display?
Yeah, it's actually on the other display.
Displays. Mirror. Show mirroring options in toolbar. I don't see it. No. It doesn't want to mirror. All right. We're going to have to play some games here, but it's off to my left, it looks like, right? All right.
Yeah, there you go.
Okay. Pretty dark. Let's try to solve the darkness problem. Come here. This is awkward. All right. Will that connect? There we go. Turn the light on. And let's focus. So you guys can see things a little bit better. All right, so I have a whole bunch of things here, and one thing that should be noted is this little guy right here right away. It's kind of hard to see in this light, but most of what you see there is actually the battery. That little postage stamp thing on top is actually the Linux computer. All right, it has both a Wi-Fi radio and a Bluetooth radio built right into it. So it's smaller than a wristwatch, and it is a full-blown Linux computer that you can do what you will with it. I typically run Node.js or Python on it. That's what I want to do. And so it's running a little Node.js app now. And this guy right here is the TI sensor tag. So it's chock full of sensors. You name the thing you want, it's probably got it in there. So it does temperature, humidity, light, noise, vibration, and a few other things. So this is the old model, this is the new model here specifically. I'll kind of show you that in a second. And then Scott did mention that some of these beacons are 3 years. So this is a 3-year beacon. Okay, and it's kind of hard to see with the light, but the battery is missing from it because I forgot where I put it. But that's it. This is all it is, a 3-year beacon. The actual radio, I think, is that little chip right there. And then you can see the antenna built right into the PCB right here. All right, so you can get 3 years out of this guy and stick it on a forklift and watch that forklift move around the plant for 3 years if you want. Okay, so let's do this. Let's get this thing started. Okay, I'm going to start that guy up, and that is my, that's my temperature sensor over there. Come back over here. No, go back over here. This is really confusing. Okay, this is 2541. So I had to click the button here, and let's get this guy going. Oh, and I'm going to click the button here. So these guys go to sleep automatically. The sensor tags, but they're going to make a connection through Bluetooth. So it's all, if you notice, the Linux box is on a battery, connected over Bluetooth here, using Wi-Fi through my router, and communicating back to my message broker. And the message broker is then outputting the data, if I can get this window to look correct. And you can kind of see it's showing up here in my browser. So looks like I got most of it working there. But so it's doing real-time temperature sensing right now and pushing that out to the broker, right? So it's Bluetooth to Wi-Fi to this box where the broker is running MQTT output router. And I'm using the MQTT NPM, which is basically a great little tool for doing all sorts of craziness. So I can just let that run in the background there. But for instance, I can send MQTT messages. Kind of come back up here where I have my other window. So let's go get this guy going. So, so if I want to turn my lamp off, turn the lamp off through an MQTT message, turn it back on. It's too dark up here. If I want to do something a little bit more creative, all right, so I have all these other robotic components and stuff like that. So let's do this. Open the robot hand, right? Send in a close. And I'm showing you these things not because these things are all that great by themselves, but it demonstrates that simple technology and any, so that turned that little other servo to the left. Watch this little guy right here. Turn him to the right. Did I do that right? Can't tell if I have a quote there or not. Oh, I have 2 quotes. That's not going to work. Yeah, let's see. Did I do it right that time? Look what it did there. Come on. Break out of that mode. There we go. Oh, I pasted that twice, didn't I? All right, let's try that. There. Let me turn them to the right. All right, there's just a handful of demonstrations, just to kind of give you a feel for what's going on. So the idea, of course, the Raspberry Pi can interface with the physical world. It has all these pins right here. You can see all these little wires. That's GPIO, right, general purpose input and output. And all you're doing is simply turning the electricity on those pins. That's the easiest way to think of it. And in the case of a lamp, a higher voltage thing, this is basically 5-volt device. An Arduino's 5-volt, this is technically 3.3, but you can also use 5 with it. The higher voltage device, I'm going to pull my relay into the view here, see a little bit. So basically, you can use the little low voltage intelligent Linux machine. Using a relay, you can drive a high voltage device. Like you want to turn a turbine on, you probably can pull that off too. So basically, there's an electromagnetic switch in here, and all he's doing is simply, hey, switch it on, switch it on, switch it on, switch it on. That's all a relay does. So with a relatively short or inexpensive kit, you can do all kinds of craziness. You can sense all sorts of things. You can collect all that data, determine what you will with it, and then, of course, actuate. So you got your sensors and your actuators, right? Actuation means go do something, take some action, and sensing, of course, is learning about the physical world about you. So you have to kind of use your imaginations at this point. Go, well, if I can speak to the physical world, what would I want to know about it, and what would I do to it? Do I want to watch temperature rising throughout my factory floor and plants because that might be important to me? Or because temperature rising typically means machine failure, right? That's what it does in a lot of electronic parts. And if I have a certain motor that's turning a certain fan, and that fan has to remove all the noxious fumes from my industrial plant, otherwise my people die, well, that fan has to be on, right? And if that fan starts to vibrate and heat up, there's a problem. It's going to die, the part's going to fail, the plant's going to shut down, I'm going to get busted by OSHA. It becomes, and all you got to do is mount a $100 sensor on it. You see what I'm saying? So a multi-million-dollar breakdown versus a $100 sensor. So I personally believe this world is going to kind of explode, as a lot of people are referring to it, when it comes to the industrial Internet of Things, as an example. And all it is relatively simple kit, as you saw here. So, you know, here, hey Dave, could you pass this around for me? Or here, do you want to hold an entire Linux server in your hand? And really, it's the size of a wristwatch.
And that's connected to the sensors how?
That particular one is all through Bluetooth. So this is the Bluetooth sensor is connected to.
So as it's passing around, can you still talk to it?
Let's see. Let's see here. And, I lost that particular window. And so that one is this guy right here. So this is the sensor. Let's see if I can make it heat up. There we go. I'm heating it up. See that second graph? All right. Now I've gone past the distance, right, that it's going to work. Yeah, it seems to have paused at this point. But, you know, that's the kind of nature of the technology. It's all battery operated. It'll run on that battery for 3 solid hours, pulling sensor data constantly. Just that little bitty battery. And this battery will last for months. And this is a coin cell battery. So people are working really hard on ultra low power devices that are very portable.
And solar power.
What's that?
And solar power.
And solar power and energy harvesting. I met with a fellow who's doing all sorts of energy harvesting research. Let's see here. Okay. Yeah, you can see that one right there paused. That's the one that's being passed around the room. Probably got far enough away that with another electrical interference, it's got a problem. But this other one's cruising along over here, as is this one, as an example. I do have a few slides I can show you real quick. And, you know, just kind of give you guys let's see if this will work for me. Okay. So as software people, I give this presentation a lot to software people. And, all right, good, close enough. So it's, you know, we deal in the world of software. We're used to things being relatively easy. If things break, we can typically fix it. Like, you know, it's all somewhere on this laptop or on this server. We can SSH in and fix it. In the hardware world, it is more challenging because it could be a physical breakdown, right? The wires are just disconnected and frayed. You got to do something about that, as an example. So you got to be prepared to handle that scenario. But we used to make software. We used to make physical things. Is there anyone actually here in the room that actually is associated with making of physical things? No hands. No, maybe a couple physical.
Barcode scanners.
Okay. So I think that's interesting. I just did this presentation for a bunch of people at the local Java user group, and there was usually 80 people. I said, by show of hands, how many people still deal with physical things? Less than 10%. Everybody is a software person now, right? Which was the core of the keynote message last night. And everyone here is in some form or fashion attached to software. But there are still people who make physical things, transport physical things, consume physical things, and really enjoy physical things. And so I just made some examples there, like utility trucks. And the thing on the left there is actually a vending machine you see in a hospital. It's for vending clothes, scrubs. And the doctors have a certain allowance, nurses have a certain allowance, et cetera. And I know a guy who used to work on these machines. That's a very important piece of equipment, right? to the hospital as an example. So if, in fact, you deal with physical things, you know, this sort of idea of the Internet of Things could be very interesting to you. This little diagram I drew here is very small. Can I do the slideshow? Maybe it'll make it a little bit bigger. Okay. Open Office. Let's see if it'll work. Let's think about it. Okay, good. Now, one too many. I got to go back. But this is just from my own career path, right? I just thought, okay, what have I done over the last 30 years or so? And I wanted to think that through. And I started out in the Chewy world, is how I refer to it now. Character UI, right? VT220 or VT100 is what we used to do. Green screen, amber screen. Maybe you were a 5250 or 3270 person. But that's what the world we used to live in.
Yeah, I remember when X Windows first came out, you got an X Window terminal, and that was a big step up.
Yeah, and you had the special keyboard, and when you had the Sun workstation, you had that crazy laser mouse, right, that didn't work except on a certain laser mouse pad.
Or that mom.
And then we went to the GUI world, right? The client server kind of kicked in, and we went to the GUI world. We had to learn about event-driven programming as programmers, and that blew our minds. What do you mean mouse clicks? There's no, you know, there's that event fires when the user clicks the mouse. It's not just a big, long procedural piece of code. Yeah, we had to rethink the way we wrote our code with event-driven programming as an example. Then we went to the web, and guess what? We went back to 5250s again, right? Block mode terminals of get, put, post, and delete. And then in the mobile GUI world, right, we had to relearn the Ajaxes type web, right, the real-time interactive type web in the mobile GUI world, and now we also have to learn things like Android and things of that nature. But the use case here is very, very critical, and I just want to put that out there for you. When we were in the Chewy world, all right, we would actually build systems. There were green screen systems or amber screen systems, and if we had a salesperson in our company, right, and they had a customer, let's say at some manufacturing plant, the customer would pick up the phone, like, old school, no wireless technology, and say, hey, sales rep, my component over here just ran out of product X. Please quote me product X. I need another batch of it so I can get my plant back online because I ran out of whatever that product was. The sales rep calls corporate, works out a deal, calls the customer back, says, okay, product X is for 5,000 tons for this much money. Here's my terms, right? And then the customer says, okay, bye, I'm ready. So the sales rep would fax in the order to the back office person, who would then type it into the Chewy screen. They would then process that ERP type order. That was the world we lived in 30 years ago. And then when we moved to GUI, right, we told the sales rep, would you get off the damn phone and the fax machine and you type it into the nice Windows user interface. You should be good enough to click a few buttons and type in what the customer wants. So the customer would call, the sales rep would type in that case. And the web GUI, we asked the customer to bypass the sales rep and enter it directly into his browser, right? That was the whole story of e-commerce. And in the mobile universe, we said, hey, Mr. Customer, you're no longer tied to your desktop. You walk around your plant floor with your smartphone and use my app to see the product that's out and order that product, and we will get the product shipped to you. You guys following me on this one? Right? This is the world I lived in, and maybe I'm in a weird world, but I had to deal with all these scenarios. Most of my background was software for manufacturing and distribution. And now we're talking about the next generation of this is the person who has the need and the sales rep and the back office person, all those people are disintermediated now. You've probably heard that term in the mid-90s. The thing that needs the stuff will directly contact your software and tell the software what it needs, and stuff will just happen. And it sounds like magic, but this is going to come true. I promise you that. Right? We actually did this in the early days of Walmart. These things did happen in manufacturing plant. And so there were brokerages and whatnot to move the transactions back and forth, but it's going to happen in a more intelligent way. So I just throw that out there at you. I talk quickly about my personal journey. So me as a software person, how do I learn all these other things? So I'm basically at the forefront of understanding what is possible. And that's why I showed you these little quick demos up front. There's a lot you can do without very, very little money. And pretty much one thing I like about the Raspberry Pi, or the Arduino, I didn't bring in my Arduino, so I have a couple over here. Anything you can think of, you type it into Google, and it's probably been answered 25 times. So you will have to work hard, don't get me wrong, but it's actually hard to stump Google in this category at this point. If you want to sense X, Y, or Z, somebody's figured it out already. And with at least these devices, that's why I like the Pi and I like the Arduino. And this Edison, which we passed around earlier, right, that little tiny Edison, this is one. Look how thin that is. And actually, the thickness is related to the fact that it doesn't by default even have a way to power it, and so I had to power it, so I had to get this little extra block for it, right? A nice little device from Intel, as an example, to compete with the Raspberry Pi. So you're going to want to figure out what all these gadgets and widgets are and understand what is possible. And then I said, make friends, right, on your journey. I've actually spent a lot of time personally with the local embedded engineering group and a whole lot of time with the local hardware group and Raspberry Pi hacker group and whatnot, because they're already there, they already understand this world. And here's one thing, how many people here consider themselves an enterprise software developer, by the way? Okay, the majority of you, which is what I would assume. The embedded engineering world is approximately 1 million embedded engineers, right? The people who build the firmware. They write the firmware for the routers, and they write the firmware for these widgets and gadgets. There's firmware on some of these subcomponents that I don't even know about, right? The guy who wrote the firmware for this thing. I'm just using it as a user. I don't have to understand that firmware. There's about 10 million enterprise developers. So you see the spectrum there that we now have to go through? We're going to go from 1 to 10. And the world now needs, by prediction, about 3 to 4 million to do this new IoT thing. Just like we needed a couple million people to do mobile. Where did they come from? They came from the enterprise workforce, right? They learned mobile. Now we're going to need another couple more million of you to learn Internet of Things. It's as simple as that, right? Not everybody will have to go. Most people can stay in desktop web, but some people will go from desktop web to mobile apps to thing apps. Okay? So make some friends and start prototyping and experimenting. At a high level, this is the architecture of how you build an enterprise IoT application. So this is very high level, at least my interpretation of it. You have your sensors and actuators out in the field, you know, doing what they need to do. You have to have some form of communication model with those sensors and actuators. So obviously we're all good with 802.11, right? We're all Wi-Fi people. That's actually not going to be the only winner like it is for the desktop. All right? It is actually one of 3 winners in my book. I'm personally a big believer in Bluetooth Low Energy, which is 802. It was 802.15.1, and Scott has done a phenomenal job deep diving on Bluetooth in particular. So you're going to see a lot of Bluetooth, especially in the consumer space, home automation and consumer space. Bluetooth is absolutely a winner. Would you guys agree with that one? So there's a third one that we might not be too familiar with because we're coming at this from a different world. It's called 802.15.4. Right? So 802.15.4 is, you know, a mesh networking protocol that you layer on with 6LoWPAN and maybe CoAP on top of 6LoWPAN. And so now you have a mesh network. And this is important because in an industrial setting, you're going to have a lot of RF interference between you and the thing you want to talk to, like we did here, right? And we used Wi-Fi. If we could use 802.15.4, we would have really killed it. Right? It would have just really worked better. So that's one thing I'm really trying to explore now is more 802.15.4 scenario because I believe that's going to have a huge future, as an example, due to the ability to route around problems.
For the devices it has to create your own network.
Yeah, exactly. So I already have some 802.15.4 radios. I just not had a chance to work with them yet, getting ready for this summit. But I plan to work on that, and there's more startups about to deliver 802.15.4 radios. So those 3 are going to be critical in the way you communicate to the thing itself. You then have to deal with the massive data ingestion, just like you saw us do in the demo, right? We had millions of data processing points that fall into our system. The message broker is a wonderful solution for that, right? You can just collect all that data. And once it's in your message broker, if you're a Java programmer, it's just Java from that point forward. It's just like any other message, right? So that's the cool thing. It's just like anything else you're used to using. So you'll probably want some sort of analytics engine. In our demo, you saw us using Spark, right, to do the actual take the raw data, understand it, and process it into business events. And then you would once you have your business data, like temperatures going through the roof, fan is wobbly, alert appropriate people, we've got a problem, whatever your use case is, or customers are going to be dissatisfied, or whatever the issue might be. You know, you then have your appropriate dashboards, your alerting system, you kick off workflows to go send a truck with the guys to go fix the problem, right? You kick off a workflow, and then you integrate with other enterprise systems. So, you know, you basically do anything you would do in normal, everyday Java land at that point. The hardest part is the ingestion point and out for us. The embedded people, though, they know all about that other world. They have no clue about the rest of this stuff. That's why I say go make some friends, right? They'll tell you exactly how much, you know, current draw, you know, milliamp is being pulled by this thing right here, and they'll have it down to the nanosecond. They'll know exactly how much battery they need. The really good ones, at least, that I've met. You know, they can talk to you about RF, you know, interference and all kinds of stuff that you're like, wow, I just want to connect with them. I didn't think about, you know, everybody running 2.4 gigahertz and all the crowding and blah, blah, you know. They deal with that kind of stuff. They also deal with something called FPGA, right? You want to really blow your mind? Go look up FPGA after you're done here. Field Programmable Gate Array. You basically can build your own CPU and make it do exactly what you want. So if you're a hardcore Bitcoin miner, you want to be an FPGA programmer now. Because you can basically you can craft your own, you know, CPU directly from Bitcoin mining is what I hear everybody's into these days. I'm not saying I am. But this is the different protocols here, right? So Wi-Fi can go direct, obviously. Also, cell is big. I have my Spark core over here. Let's see here. I don't have it booted up, and I'm not using it at the moment, but I'll just show it to you. And then, oh great. This might work. Let's see here. Yep. So this is my Spark core. Try to so you can see the light. So basically, that's the radio on top. This is a Wi-Fi chip and a microcontroller built into one. You have 2 classes of smart things, by the way. You have the microcontroller and you have the Linux box. This is the way to think of it, right? So you can see that there's my Here's my Intel Edison Linux box. It's the same size as the microcontroller. The real distinction is your Linux box is a Linux box. It's not truly a real-time operating system. It allows for interrupts, right? You know, if someone's downloading a big cool video from your Linux box, it's going to pause and download a quick big video. If it's supposed to be actuating a fan that's keeping the plant alive, that's problematic. So these MCUs, right, microcontrollers, are widely used throughout all the operations in your car. If you need an airbag to trigger at a certain point, you don't want the fact that you're streaming, you know, internet radio to stop your airbag from coming out, right? So that's the MCU world. So this is an example of that. And I mentioned them because they also have a cell-based version that's coming out right now. It's pretty awesome if you think about it. So a Wi-Fi-based microcontroller, think of this as an Arduino with Wi-Fi. The new versions are $19, and they're about to deliver cell versions. So if you have propane tanks scattered around your geography, you now can communicate with all of those and find out exactly how full they are without sending a person out to verify how full they are, as an example. So I really like what I've seen with the Spark guys. The downside with the Spark guys is they want to put everything in their cloud, which is, I think, unfortunate. Okay? I'll just kind of let's kind of skip, I'll skip through the jokes so we don't have to spend time there. The only thing I'll say, and you might think about history lessons. If you've been around the industry for a while, the moment we are at right now, in my opinion, honestly, is we're in the Banyan Vines, netware, and there's TCP/IP things starting to get popularity. That's where we are right now, right? There's a lot of churn happening in space. There's a lot of proprietariness happening in space, and there's the thing called TCP/IP is not yet won today. Today, would you ever use Banyan Vines for anything, right? Or SNA or IPX, SPX? No. So we're at that moment now. There's all these different ways to communicate the things. Every vendor that produces the hardware has a proprietary stack and proprietary API so they can lock you in, but that world is about to fundamentally change, right? So if you're buying stock in some of these companies, you better hope they have an open strategy. This is like, you know, when the Unix world got exploded by Linux, is how I look at it. Okay, I'm trying to make sure we stay on time. This is a series of protocols and terminology you want to start getting your head around. Obviously, you know about Wi-Fi and things like that, but I mentioned 802.15.4, and 802.15.1 was the old spec for Bluetooth. Now it's just called Bluetooth, right? Got to go by the marketing name. It's not really 802.15.1 anymore. 6LoWPAN, I think, is particularly interesting. I feel that it's going to be very interesting, especially 6LoWPAN over mesh networks. I think that's going to be huge. And then CoAP, on top of that, is usually a nice application-level protocol. Think of that as your HTTP on top of the stack. MQTT, of course, is a de facto winner at this moment, if you will. That's why we use it for all our demonstrations. It's widely used. It's widely supported by a lot of parties. But I do think CoAP is coming on strong. And a lot of people will simply just use REST. There's a whole bunch of people in the world right now just using REST to communicate with things. That's cool, but REST does mean you got a full HTTP stack, right? A full TCP/IP stack underneath that, and that means it's harder to put that on a battery. It just does not last, right, on the battery. It burns too much battery. Wi-Fi burns too much battery, and that's the problem with it. So that's why another reason why 802.15.4 and Bluetooth are really starting to win out, because you can run them on battery for days, weeks, years, right? That's what people are trying to do. They're trying to get years out of their Bluetooth battery operating devices. What else we got here? This long, you guys are feel free to email me, Burr, Red Hat, and I'll give you the slide. At one point, I was trying to come up with a PRD, right, a template for a PRD, product requirements document. What questions do you have to have answered if you want to build an Internet of Things device? And there's a lot you got to think through. But there's a lot if you do anything architecturally in a big, complex system. In this case, it involves things like distance from the thing I need to talk to, and you got to think about physicality. You know, does it need to handle heat? Does it need to be waterproof? Does it need to be, live out in the sun? How do I power it? How do I communicate with it? That's where the complexity comes in. Power and communication. This slide is kind of neat, so I'll let you guys kind of eyeball that one. But this is the world that's happening right now. This is not what I call traditional vendor space. There's all these traditional vendors, like Texas Instruments is on my slide here, but Texas Instruments, Silicon Labs, Freescale, Nordic Semiconductor, there's all these big giant companies that do chips. Chip manufacturers, silicon vendors, but they don't rock developers. And so now what's happening is there's a whole cadre of developer-oriented startups who've taken the chips and made it a developer-facing package, like the Spark team. Now they're called Particle, as an example. That's exactly what Arduino did. That's exactly what the Raspberry Pi team has done. They've exploded in popularity. Raspberry Pi is well beyond 5 million units at this point. I mean, they're like an unstoppable force, right? They're just gaining momentum every month that goes by. But I do like a lot of the ones you see here. Light blue bean, I have several of those. Bluetooth Low Energy runs on a watch battery, and it has a temperature sensor and accelerometer built in. You also have the proto board. You can solder on your own buttons and widgets and gadgets. It's a pretty awesome little toy. We shouldn't call it a toy. It's a pretty awesome little programmable microcontroller. It's an Arduino with Bluetooth. And there's all kinds of awesome use cases for that particular item. There's, we talked about the Raspberry Pi. Onion Omega in the top right there, I backed them on Kickstarter, so I'm waiting for that one. So yet another programmable Linux machine on a chip, right? So the Linux world is exploding in this space. So you got your Intel Edison, your Yocto distribution, you got your Debian or Raspbian on your Raspberry Pi, you got the OpenWRT on the Onion. But basically every month now, there's a new startup building yet another powerful Linux machine, the size of a postage stamp or the size of a quarter, and it's getting to be pretty amazing, right, what you can do with this. You can SSH in, like you saw me doing, and run code on it. I've been talking to robotics people. They love this, because historically, they had to chase the robot around with a serial cable and do debugging. Now they can SSH into the robot and just get the logs out of it and figure out what the hell's wrong with it. And that may seem trivial, because we're software people. And this is a huge win for them. They are tired of chasing robots around, literally. You know, in a big manufacturing plant, they got to go walk up, plug shit in, and look at it, right? Now they don't do that anymore. So I've had some pretty funny conversations there. This is a great little thing I'll leave you with, because we're basically out of time. But I want to say connectivity is still a challenge, just like the 90s, banding lines, netware. But this is great. I found this from March 20th, 1995, Rich Tennant in Computer World, when we used to read Computer World. Remember that? Yeah, we don't read them, I guess, that much anymore. But now this is one engineer explaining to the other engineer how he has his home automation system. Now when someone rings my doorbell, the current goes to the scanner that digitizes the audio impulses and sends the image to the PC, where it's converted to a PIC file. The image is then animated, compressed, and sent via high-speed modem to an automated phone service that sends an email message back to me to tell me someone was at my door 40 minutes ago. I thought that was, it's 20 years old as a cartoon. We're still kind of here, aren't we, right? But this world is absolutely fundamentally going to change. Google and Apple and other parties are investing heavily. The chip vendors have kind of woken up to this concept. The startups are all well-funded and cranking out really, really cool innovations. So it is going to happen. And I'm hoping that you saw in our demonstration here this week, what we wanted to show, let me get over to the right window. We wanted to be able to show you real business value. The right one. Oop. Oh, what happened? Come to the foreground. Dun. Oh, great. It wants to be in the background.
Will you close the presentation?
Yeah, exactly. It's hard to steer over your shoulder, man. Go away. Would that help me? Oh, great. Get a black screen instead. Man. How's this projector been set up? Okay. LibreOffice, go away. Die. There. Oh, it is not going to let me display this.
Yeah, it's trying to
Oh, there it is. All right. But this is what we showed last night. I made a quick recording of it just so you could kind of see it. But this is the actual, oh great, it's halfway through its cycle. Back to the beginning. Okay, one more time. But this is the business value we were trying to gain, the business data, if you will, from collecting all those, the traffic information, right, using the Bluetooth signal. You can kind of see everybody shows up in the morning around 8 o'clock, goes to breakfast, goes to the keynote for DevNation. You can kind of see them on the 3rd floor, right? And then they start heading to breakout rooms down here in the 200 levels. And then after a while, as it gets throughout the day, we do lose people every now and then because we don't have scanners everywhere. We just had them around the 200s and the 3rd floor and the general session room, so you will see us lose some people. But as we get closer to the 4 o'clock time frame, right, you will see them start showing up. And there was an afternoon keynote, so that's why you see a little burst up in the 3rd floor. But you see them start collecting in the keynote room. And then you see us run our keynote, so that's where the majority of people are. And then we've done our keynote. It's now going in the evening. And people kind of go back to different breakout sessions and whatnot. And eventually they just go about the business and go home. So this might seem kind of crazy, but this is actually very valuable data if you're a marketing company that wants to do conference management, things like that. But this is what we can do when Scott and I bought this stuff. He did all the firmware updates to those 300 different beacons, right? So it can be very inexpensive and very powerful. So hopefully you guys can at least feel comfortable with that. And I think we're out of time at this point, but Scott and I can be around for questions for a little while longer.
And we have a hackathon tonight, but I think you need to register if you haven't already. So I think there's still spots available.
You get to build